Hey everybody, I'm back with another calculus optimization problem. Here we have a farmer with 1,000 meters of fencing. They want to enclose a rectangular region. It needs to be divided into 3 pens as shown. So whenever we're doing an optimization problem, we always want to start out with a picture, if at all possible. Here we already have one, so check that box. The second step is to write an equation for the thing you're trying to optimize. As you're doing that, you're going to be choosing your variables. A lot of times, the thing you're trying to optimize, in this case area, will strongly suggest appropriate variables. We know area is length times width, so those are going to be good choices for our variables here. Let's call the length and the width x and y. So x will go this way, and y will go this way. Fantastic. In calculus, we don't have the ability to optimize a function with 2 variables. We have to get one of them out using substitution. In order to do that, we're going to need to get another equation relating x and y. Hint, look back at your problem, find a piece of information you haven't used yet. That's probably going to help you relate those 2 variables. So here, it's that 1,000 meters of fencing. So we know that we have 1,000 meters of fencing, and that's going to equal the sum of all these lengths. So we have these 4 vertical bars for y, and we have 2 horizontal bars, so 2x. So I'm going to solve this for x and plug in here to get an equation just in terms of y. I'm going to do that by moving the 4y over to the other side, subtracting 4y from both sides, and then dividing by 2. So overall, I get that 500 minus 2y is equal to x. Now I'm going to take this equation here. Wherever I see x, I'm going to replace it with what x is equal to, 500 minus 2y. Overall, I get that the area is equal to 500 minus 2y times y. So that's the function I'm truly trying to optimize. Let's make a little space here. We'll leave the picture. We'll want to use that. Once we have the function we're trying to optimize, we have to write its domain. All of the techniques that we have in Calculus 1 for optimizing, for finding absolute maxes and absolute mins, are going to require that we know the domain of the function. And you have to do that using not only the formal algebra, but also real-world considerations. Here we just have a polynomial. Its domain is all real numbers. We also have to think about what values of y actually make sense given the real-world considerations. So what do I mean? Well, first of all, y is the width of the pen. That can't be negative. What about an upper bound? Well, we know that the farmer has 1,000 total meters of fencing. So even if they don't use any going left and right, if they only use it for these vertical parts, they're going to have that 1,000 meters of fencing to divide into those 4 pieces. That's 250 meters apiece. That's the domain on which I want to optimize this function. Now I'm ready to actually do some calculus. I want to take a derivative. I want to find critical values. Before I find a derivative, I'm going to distribute this through to make the work a little bit easier. So A is going to be equal to 500y minus 2y squared. Let's differentiate. A prime is 500 minus 4y. Critical values mean either the derivative does not exist or it's equal to 0. This is another polynomial. It's never going to not exist. So we just need to know where it's equal to 0. I set 0 equals 500 minus 4y. Add 4y to both sides. 4y equals 500. And so y is 125. That's the only critical value I have here. Now, the closed interval method says the absolute max and absolute min can only occur at critical values or endpoints. So I can take the critical value and the endpoints, plug each of them into the original function, and just see which one of them gives me the biggest area. The biggest of those three will be the biggest period. So I need to do a of 0, a of 125, and a of 250. The first and the last of these are very easy. When y is 0, I get 0. And when y is 250, I also get 0. Then I have to plug in 125. I get 250 times 125, that's 31,250. Clearly, that's the biggest of the three. That tells us that the maximum possible area that the farmer can enclose is 31,250 square meters, and it's done by making the pen have a width of 125